to illustrate the idea of basis functions, let me actually give the special, give you this specific case. Okay, so let me say I have the domain and I split the domain into 3 elements. And my U can be anything that is linear within every single element and also continuous. All right. In this case, I'm going to claim that any U, okay, any U of X can be represented as a linear combination of 3 basis functions. I'm going to tell you it's U at 0. I'm just going to call it U0. It is actually going to be the value of U at 0 times phi0 as a function of X plus U1 times phi1 as a function of X, right? So basically this value here is not phi. This value here is U0. This value here is U1. This value here is U2. The y coordinate here is U3. Okay, and goes on. U2 times phi2. So the question I want to ask you is do a little bit of detective work and try to figure out what is phi0, phi1, phi2, and phi3 as a function of X. What do you think? If I'm saying I can represent any U as a linear combination of such basis functions, right? So these are basis functions. What do you think such basis functions look like?
Linear?
Yes, I mean, this basis function also has to be linear. That's right. Because if these functions are not piecewise linear, it's a little bit hard to imagine when I perform linear combination of them, it'll magically become linear, right? Okay, I'm going to give you a hint for the very first function. The very first function phi0 is going to look like this. Its value is going to be 1 at x equal to 0. And it goes linearly down to 0, and then it'll stay 0 for the remaining of this domain. This is the function form of phi0x. Can somebody try to guess what phi1x would look like? Well, phi1x actually does something pretty similar to phi0 of x, right? It actually starts 0 here, and it increases linearly to the value of 1 at the first grid point. And afterwards, it decreases linearly back to 0 at the second grid point. So that is, and it stays 0 for the rest of the domain. That is going to be the form of phi1x. Okay, now you can see that simply by combining phi0 and phi1 with their respective coefficients, you can recover the first part of this arbitrary function, right? That satisfies the simplified constraints. You see, at x equal to 0, I have my u0 times phi0, which is 1. So the value is u0. And the coefficient on phi1 is u1, but the value of phi1 is 0 at this point. So if I add u0 phi0 and u1 phi1, I'm going to get u0 when x is equal to 0. On the other hand, when x is equal to the first grid point, the right side of the element, my phi0 is going to be 0. My phi1 is going to be 1. So the linear combination u0 times phi0 plus u1 times phi1 is going to give me u1 instead of u0. So the value here is going to be u1, right? mean, just by doing a linear combination of these two basis functions, I recover the first part. Now, what do you think is the phi3? All right. What do you think is phi3? Oh, phi3 is actually a function that is starts to be 0 in the first element, and then it slowly increases to the value of 1 at the third grid point, and then linearly decreases back to 0. So that would be phi2 of x, and the phi3 of x is going to be something like this. So phi3 is going to stay 0 for this rest of for the first two elements, and increases linearly to the value of 1 here. So that'll be phi3 of x. All right, does it make sense? I mean, the reason I'm constructing these functions is because once you have these 4 basis functions, or if you have many more elements, right, you can construct as many of these basis functions. You may call them hat functions, right? These are hat. You can call them hat basis functions, and these are going to give you. These are going to give you, by performing linear combination of them, you can construct any piecewise linear and continuous function you want. All right, so this is basically what we have done last time, right? Restricting our solution into a set of piecewise linear and continuous functions. And we are just representing it in a little bit more convenient way. And why do we do that is going to be clear, pretty clear later on. And the second thing we do is by looking again at the weak form. And we also want to restrict the test function v into a similar constraints, right? We also enforce the weak form for a subset. Actually, I should call it subspace, because the subset forms a linear space, forms for a subspace of test functions V that satisfies the same or in some cases similar constraints.